Pierre Cartier, a visionary mathematician. I'm Dr. Samuel Alan Alexander reading the article Pierre Cartier, a Visionary Mathematician by Alain and Joseph Kouneiher in the 2025 Notices of the AMS. This article reflects on the life and mathematical contributions of Pierre Cartier, a distinguished figure in the 20th and 21st century mathematics. As a key member of the Bourbaki collective, Cartier played a pivotal role in the formalization and modernization of mathematics. His work spanned fields such as algebraic geometry, representation theory, mathematical physics, and category theory, leaving an indelible mark on the discipline. Beyond his technical achievements, Cartier was celebrated for his intellectual generosity and humanistic approach to science, shaping not only mathematical thought but also the broader cultural understanding of the field. Pierre Cartier passed away on August 17, 2024, leaving behind an intellectually rich and profoundly human legacy. The first word that comes to mind when thinking of Pierre is universality. He was an extraordinary mathematician whose remarkable intuition impressed many. Alexandre Grothendieck himself, a legend in the field, recognized in Récoltes et Semées Cartier's unparalleled intuition, capable of penetrating the most varied subjects with remarkable clarity and depth. Pierre dedicated his life to mathematics, to which he contributed a vast treasure, both through his personal discoveries and the ideas he generously shared with the community. Figure 1. Pierre Cartier. Pierre Cartier was born on June 10, 1932 in Sedan, France. After completing his secondary education in Sedan and preparatory classes at Lycée Saint-Louis in Paris, he was admitted to the École Normale Supérieure in 1950 through the mathematics competition and defended his thesis in 1958 under the supervision of Henri Cartan. Officially, at the beginning, his thesis advisor was Roger Goderman. However, he felt more inspired by the work of Cartan and especially André Weil, so he changed his research topic, derivations and divisors in algebraic geometry. The best result of my thesis, The Duality of Abelian Varieties, was a problem posed by André Weil in his book on abelian varieties and algebraic curves. Cartier became a member of the Bourbaki group in 1955 at the age of 23. Wow, that's young for that. And remained so until 1983. After holding a professorship in Strasbourg during the 1960s, he was appointed research director at the Centre National de la Recherche Scientifique. He was a permanent visitor at the Institut des Hautes Études Scientifiques in Bourges-sur-Yvette, where he left a lasting impact, and served as a visiting professor or researcher at Princeton, the École Polytechnique, and various other institutions. From 1988 to 2002, he was a professor at the École Normale Supérieure. He is best known for his work in algebraic geometry, representation theory, homological algebra, and category theory. His interest in mathematics emerged very early, particularly after reading Hermann Weyl's work on group theory and quantum mechanics at the age of 18. It was undoubtedly my reading at the age of 18 of Hermann Weyl's classic work on group theory and quantum mechanics that had the greatest influence on the course of my subsequent mathematical research. In it, I discovered how the beauty of a fully developed mathematical theory can be combined with the profound physical necessity and the importance of the connection drawn between seemingly unrelated fields. Through contact with eminent scholars who taught mathematics at the École Normale Supérieure and later with Nicolas Bourbaki, I definitively oriented myself towards pure mathematics without disregarding the value of analogies drawn from physical sciences, the importance of applications, or the assistance provided by a well-controlled intuition. If the list of my publications gives the impression of incessant wandering from algebraic geometry to probability theory, from algebra to quantum mechanics, from group theory to numerical analysis, or from number theory to combinatorics, it's because I have strived to perceive the multiple consequences of a few general ideas that I have constantly revisited. I've been more interested in the discovery of new truths than in the meticulous cultivation of a field already well explored. Ah, a man after my own heart. For years, Pierre was a pillar of the Bourbaki collective, playing a key role in transforming 20th century mathematics and helping to propagate the language and methods that have become standard in modern mathematical research. He was one of the rare individuals who mastered the full breadth of Bourbaki's work, reflecting his deep belief in the power of structure and generality in mathematical thinking. Cartier dedicated a significant portion, 1/3 according to him, of his mathematical activity to drafting Bourbaki's books. For instance, chapters 4 to 6 of the famous books on Lie groups and Lie algebras benefited from Cartier's idea to base everything related to root systems, file groups, etc. on symmetries with respect to hyperplanes in a vector space. He also delivered about 40 Bourbaki seminars, reflecting his commitment to the collective and to the transmission of knowledge. Pierre Cartier's contributions are as vast as they are varied, spanning fields such as algebraic geometry, number theory, category theory, distribution theory, and mathematical physics. Through the concepts he created, many of which bear his name, such as Cartier divisors and algebraic geometry, he provided the correct conceptual framework for understanding key notions. For instance, in the case of divisors, his idea, derived from Henri Cartan's work in analytic geometry, of local sheaf theoretic formulation, applies even in situations that would be inaccessible to a more naive notion of divisors. He was the first to uncover the special properties of the de Rham complex infinite characteristic, offering groundbreaking insights into its behavior in this setting, and introduced the Cartier operation in the differential calculus of algebraic varieties in positive characteristic. This revealed a radically different scenario compared to characteristic 0. Cartier's work in the theory of commutative formal groups represents a foundational contribution to algebraic geometry and number theory. His introduction of Cartier's formal groups provided a deep and flexible framework for studying algebraic curves, group schemes, and their associated deformation theory. In essence, Cartier formal groups offer a language for understanding the infinitesimal behavior of varieties and schemes over fields, rings, and more general bases. Regarding his involvement in Grothendieck's work, Cartier writes, all those concepts such as Cartier divisors, the Cartier operation on differential forms, the Cartier duality of group schemes with finite group schemes, and particularly inseparable descent translate seamlessly into Grothendieck's new theory of schemes. By combining his methods with mine, Grothendieck obtained a very simple proof of the completeness theorem for linear systems of divisors. He adds, in 1966, I glimpsed the possibility of extending Dudon's structural theorems to this new framework. My aim was initially to generalize the construction of one-dimensional formal groups introduced by Lubin and Tate, and to express it independently of the choice of a coordinate. I first demonstrated that the essential property was the existence of lifting of the Frobenius operator, and I was able to obtain a complete description in terms of modules for the corresponding class of formal groups. Using these results, I was able to fully resolve a series of problems formulated by Grothendieck in connection with his theory of crystals. Hopf algebras, group theory. Cartier had a guiding thread in his work that revolved around groups and Hopf algebras. He viewed Hopf algebras as a powerful tool for understanding various algebraic phenomena. His research often focused on their applications in algebraic topology, representation theory, and mathematical physics. The duality in Hopf algebras, where every algebraic structure has a corresponding coalgebra structure, resonated with Cartier's broader mathematical philosophy, which emphasized the interconnectedness of different fields of mathematics. He said, I have never abandoned group theory. For me, it remains the central point of everything I've done. In my opinion, the book that everyone should have read is Group Theory and Quantum Mechanics by Hermann Weyl. It's a text that I still read today with the same interest. Group theory has the advantage of allowing one to do physics in the way Weyl proposed, so it's an important tool in physics. It's also an important tool in geometry, of course, after the works of Alain Cartan, the father of Henri Cartan, and even before that. It's a crucial tool in arithmetic, as demonstrated by Andre Weil. For me, it's as if I have a fortress, the fortress of groups. I can explore here and there, enter through another door, but in the end I always return to my fortress. Cartier's early interests and original results focused on characterizing the enveloping algebra of the algebras through the properties of its filtration and coproduct, establishing the algebraic foundation for the local theory of Lie groups and its extension to formal groups. Another central idea of his geometric theory of Weyl groups. His perspective is that the classical theory should be understood as the study of groups generated by symmetries relative to linear varieties. At a Bourbaki Congress in Pelvoux, Pierre Cartier introduced the axioms of root systems, which play a key role in the chapters on Lie groups and Lie algebras. One of the recurring themes in his research was the relationship between the representations of a Lie group and those of its Lie algebra, specifically the problem of infinite-dimensional unitary representations. Along with Dijksmuir, he extended Harish Chandra's results to the case of arbitrary Lie groups in a Banach space. These results caught the attention of mathematical physicists who, following in the footsteps of Hermann Weyl and von Neumann, were analyzing communication relations in quantum mechanics. Commutation relations in quantum mechanics. Cartier introduced distribution vectors for infinite-dimensional representations, which were subsequently used in functional analysis and quantum field theory. In fact, Ed Nelson was able in 1959 to remove an unnecessary hypothesis by using entirely new methods in the theory of processes, stopping times and the strong Markov property. This triggered Pierre's interest in probability theory. In 1964, Cartier reported on the early work of the Russian school, Galfand Milnos, on stochastic processes in infinite-dimensional vector spaces. He introduced the class of standard spaces into the theory. in which measure theory does not present the monstrosities that had so hindered the development of process theory. His student Fernique proved in his thesis that all functional spaces are standard. Cartier observed that these standard spaces were none other than the non-metrizable Luzin spaces, and that the entire classical theory of Luzin and Sulin never relied on the metrizability hypothesis as initially assumed. Cartier's collaboration during this period with P.A. Meyer and L. Schwartz culminated in the Bourbaki volume that concluded this series on integration and measure theory. Cartier then turned his attention to the Markovian properties of random functions or distributions with multiple parameters. His work resolved the controversy between Paul Levy and McKean, favoring the latter, and uncovered the flaw in Paul Levy's reasoning. These same random distributions found applications in the constructive theory of quantum fields following the work of Nelson and Cartier himself. In his work on the path integral formulation of quantum mechanics and quantum field theory, Cartier, in collaboration with Cécile de Witt-Moret, sought to place this crucial concept on solid mathematical ground. By integrating methods from algebra, geometry, and analysis, Cartier helped to clarify the path integral's use and its connection with other areas of mathematics, such as stochastic processes with functional integration. We'll return in section 1.3 to another major contribution of Pierre to mathematical physics, namely his cosmic Galois group in renormalization theory. On the theory of formal groups. Among Cartier's original contributions to group theory are his results related to formal groups following Dieudonne's publications in 1954 and 1959, which established the theory of formal groups. This work marked a return to the roots of Lie theory by studying power series that express multiplication near the origin of a Lie group. Dieudonne, especially in the case of commutative groups, obtained a series of new results. Cartier's aim, building on H. Cartan's results in algebraic topology, was to reformulate Dieudonne's theory in terms of linear duality. Cartier emphasized the importance of the coproduct in Dieudonne's hyperalgebra, providing an intrinsic formulation of the notion of a formal group, establishing its equivalence with that of filtered bialgebras, and extending the framework to obtain the kernels of homomorphisms. Building on Dieudonne's work, Cartier observed that p-adic matrices were what Weil had lacked to complete the theory of abelian varieties. Upon reading the unpublished manuscripts on formal groups that Dieudonne had shared with me, I had the sudden insight that his p-adic matrices were precisely what Weil had been missing to complete the theory of abelian varieties he had just developed. At the same time, Grothendieck was beginning to completely revolutionize algebraic geometry. Under Jean-Pierre Serre's guidance, Cartier resolved all the issues left unresolved by Weil, including the biduality of abelian varieties, the absence of torsion in the divisor class group, also resolved by Barsotti, and the representation of homomorphisms of abelian varieties, all while employing the technique of studying isogenies, especially in the inseparable case. However, these works gained their full significance only during the introduction of group schemes by Grothendieck. During this period, Cartier introduced several key concepts: Cartier divisors, the Cartier operation on differential forms, Cartier duality of finite group schemes, and most notably, inseparable descent. All these concepts were seamlessly integrated into Grothendieck's new theory of schemes. By combining his methods with those of Cartier, Grothendieck provided the proof of the completeness theorem for linear systems of divisors. In 1966, Cartier recognized the possibility of extending Dieudonne's structure theorems. The essential progress was the introduction of curve modules associated with formal groups and the notion of a typical curve. This novel concept retrospectively explained the arithmetic properties of the classical exponential series and, in particular, the existence of the Artin-Haas exponential. It also offered a flexible interpretation of the Dieudonne module and allowed me to refine known theorems on Witt groups. The universal typical curve in a Witt group plays a central role in these demonstrations. Cartier's theory of commutative formal groups and his work on the typification of curves through the introduction of what are now known as Cartier's formal groups were pivotal. These results laid the groundwork for understanding the structure of formal groups and their role in number theory and algebraic topology. His introduction of the global Witt construction, an advanced technique that unifies various local constructions into a coherent global framework, remains a cornerstone in the study of algebraic structures. Quantum groups. Cartier was deeply interested in the theory of quantum groups, which are deformations of classical groups that can be studied within the framework of Hopf algebras. This work not only broadened the theoretical landscape of algebra, but also had significant implications for mathematical physics, particularly in the study of symmetries and integrable systems. Drin-filled quantum groups, for example, are crucial for understanding how algebraic structures encapsulate quantum symmetries. Cartier expressed his deep attachment to Hopf algebras when describing the most important scientific moment of his life, the presentation he gave at the International Congress of Mathematicians in 1986 in Berkeley, and the new lines of research it opened. At the Congress, I presented on behalf of Drinfeld, who was invited but couldn't attend to the Soviet regime. On the first day, the Russian president of the International Mathematical Union handed me Drinfeld's English manuscript, unsure of what to do with it. There was also a text from Manin, and he asked if I could replace one of them. After a brief thought, I chose Drinfeld's. He then informed me that the presentation was scheduled for that afternoon. I took the manuscript and said, "I'll try." I explained the situation to Kaplansky, the American president of the organizing committee, who helped by locking me in a room with sandwiches and coffee. I had 6 hours to prepare. Although I was familiar with Hopf algebras, the material was new, and by the time I gave the talk, 400 people had gathered to listen to Drinfeld, which meant me. In the following days, I distributed as many copies of the text as I could, made using simple methods. At that time, I was nearing the end of my mathematical research program and was in a period of waiting. I realized that quantum groups were something entirely new that could be approached with techniques I had previously used, like Lie groups and differential geometry, which I knew well. There was also motivation from physics, even if not always apparent, which reoriented my interests for a good 10 years. In fact, I still organize a seminar at the École Polytechnique called Quantum Groups and Poisson Geometry, which continues this work 20 years later. The cosmic Galois groups. In the realm of mathematical physics, Pierre Cartier had a long-lasting interest in quantum field theory. He proposed the idea of a cosmic Galois group underlying the symmetries of the renormalization process, while the traditional renormalization group could be viewed as a one-parameter subgroup of this larger cosmic Galois group. On this idea, he writes, "My notion of a cosmic Galois group rose from my reflections on mathematical physics. I drew particular inspiration from the work of Reference 13, who redefined the renormalization process, a technique for eliminating infinities and divergent integrals linked to Feynman diagrams. They introduced a new group structure to describe the intricate relationships in these calculations. At the same time, my mathematical research has focused on series and integrals involving special numbers like powers of pi and values of the Riemann zeta functions. These relationships are governed by a symmetry group that resembles Grothendieck's motivic Galois group. I began to see a striking analogy between this group and the Kouneiher group, suggesting that they might be two variations of the same group, influencing both the mathematical and physical aspects of the problem. The motivic Galois group deals with the automorphisms of certain transcendental numbers, which are similar to the constants appearing in Feynman diagram computations. This observation led me to interpret the group in Reference 13 as a symmetry group governing the fundamental constants of physics. In the standard model, these constants are often adjusted empirically without much mathematical explanation. I believe that this group could express new symmetries among these constants, which might have significant implications for cosmology. My ultimate dream is to unite the ideas in Reference 13 with the motivic Galois group, even if for now it's still an ongoing research program." It took a lot of work and time to obtain a concrete realization of Pierre Cartier's idea of the cosmic Galois group, as well as its action on the coupling constants of renormalizable physical theories. The first step, following the introduction of the Hopf algebra of Feynman groups, was the realization that the renormalization process is in fact in the dimensional regularization scheme, identical to the Birkhoff decomposition in pure mathematics, which occurs in the classification of vector bundles on the sphere. Once this result was obtained, it again took time using the Riemann-Hilbert correspondence to realize that there exists a universal Hopf algebra, Cal H, behind all these computations. This is the graded dual Cal H of the universal enveloping algebra of the free-graded algebra generated by elements of degree n for each positive n. Let blackboard bold U be the affine group scheme associated with Cal H, and let Cal H and blackboard bold U star equals blackboard bold U twist product blackboard bold GM be its semi-direct product by the action of the multiplicative group by the grading. It follows that this group acts on the coupling constants of any renormalizable physical theory, thus providing the best model for the cosmic Galois group. It gives a concrete realization of the symmetry group of physical theories and has a tantalizing similarity with the motivic Galois group of mixed-state motives. Curiously, one of Cartier's most cited results is the so-called Cartier theorem often discussed in the context of algebraic groups over fields of characteristic 0. This theorem, a key result in algebraic geometry and group theory, asserts that algebraic groups over fields of characteristic 0 are smooth. It plays an important role in the study of algebraic groups, as smoothness is a fundamental property with significant geometric and arithmetic implications. In this context, smoothness means that the algebraic group is a smooth variety. Its tangent space at every point is well behaved, which roughly implies that there are no singularities in the variety. This result is foundational in the theory of algebraic groups because smoothness is a desirable property in geometric structures, ensuring that algebraic groups can be analyzed using standard differential geometric tools as they behave well locally, and that they exhibit favorable properties in representation theory. The fact that this theorem is only mentioned as a footnote in one of Cartier's papers is due to its relatively technical nature and the fact that it was not central focus of his work at the time. Although the proof of smoothness for algebraic groups in characteristic 0 was not a primary goal in that paper, it was still an important result for the completeness of his theory, which is why it is briefly noted. Cartier's many key ideas offered to others. Pierre Cartier's influence extends well beyond the concepts associated with his name, as his intellectual generosity fostered significant collaborations with his contemporaries. Notably, he provided André Weil with key ideas for proving fundamental results in number theory using the local compactness of the topological ring of Adels. Cartier's insights certainly influenced Weil in basing his book Basic Number Theory on the local compactness of the ring of Adels, which contains a global field as a discrete and co-compact subfield. Cartier also advised Grothendieck to use prime ideals instead of maximal ideals when defining the spectrum of a ring in algebraic geometry. Wow, that's extremely major, as prime ideals are the only ones compatible with morphisms. In classical algebraic geometry, points of an algebraic variety correspond to maximal ideals of its coordinate ring, while prime ideals correspond to irreducible closed subsets. The spectrum of a ring, spectrum of big A, therefore includes standard points associated with maximal ideals and generic points linked to irreducible closed subsets. The idea of viewing irreducible subsets of an algebraic variety as points can be traced back to Italian algebraic geometers in the early 20th century. Another clarification brought by Cartier to Grothendieck's work also concerns the concept of schemes. In algebraic geometry, schemes are mathematical objects that generalize algebraic varieties. Grothendieck introduced this concept in the late 1950s, defining schemes as entities that encode information about the solutions to polynomial equations through commutative rings. However, to address the complexity of these objects, Cartier proposed a more abstract and powerful perspective. He suggested viewing Grothendieck's schemes as functors from the category of commutative rings to the category of sets. This innovative perspective significantly impacted algebraic geometry by providing a more abstract and robust understanding of schemes. The significance of this proposal lies in its universality and generalization. This functorial approach allows the concept of a scheme to be extended to more general situations, thereby facilitating the study of the properties of these objects in various contexts. This perspective also paves the way for applications in other areas of mathematics, including topology, number theory, and even theoretical physics, where similar constructions often prove useful. It's worth noting that Chevalier had already used this idea in his 1956 paper on finite Lie groups, in which he defined an algebraic group as a function from rings to groups. The introduction of group varieties in transcendental number theory by Serge Lang followed a conjecture of Cartier, who asked whether it would be possible to extend the Hermite-Lindman theorem from the multiplicative group to a commutative algebraic group over the field of algebraic numbers. This is the result that Lang proved in 1962. At that time, there were a few transcendence results by Siegel and Schneider concerning elliptic functions and even abelian functions. However, Lang's introduction of algebraic groups in this context marked the beginning of several important developments in the subject. More precisely, in reference 28, Lang proved Cartier's conjecture, which states that if big G is an algebraic group over a number field big K and alpha in the Lie group of big G quantity of big K is such that T maps to x sub big G of T alpha is not an algebraic function, then x of alpha is transcendental over big K. For big G as a linear group, this reduces to the classical result concerning the exponential function. The novelty comes from the nonlinear case. When big G is an abelian variety, Lang's result represents a transcendence result for values of theta functions. Lang derived this theorem from his transcendence criterion, which generalizes the method of Gelfand and Schneider. The other facets of Pierre Cartier. Beyond his technical contributions, Pierre Cartier was a passionate advocate for the philosophical and humanistic aspects of mathematics. He recognized that mathematics is not merely a collection of theorems and proofs, but a human endeavor that reflects creativity, beauty, and the search for truth. His writings and lectures often explored the broader implications of mathematical ideas, touching on their philosophical foundations and connections to other fields such as physics and philosophy. Regarding his interest in the epistemology and philosophy of mathematics, Cartier made the following remark. What attracts me to the epistemology of mathematics is understanding how mathematics is woven into civilization. I'm interested in how mathematical concepts emerge from societal concerns reflecting the zeitgeist. One of my students specialized in the history of mathematics in China and worked on her thesis with me and my sinologist brother. André Weil sparked my interest in the history of mathematics, teaching me to view past mathematicians like Euclid, Archimedes, Fermat, Euler, and Gauss as contemporaries. Hermann Weil's writings also influenced me, prompting a desire to explore the relationship between physical and mathematical concepts from a philosophical perspective. Recently, I've focused on the history of categories, partly because I've contributed to their development and can draw on my memories. This area of mathematics closely aligns with philosophical issues, which I find more compelling than formal logic itself. The central question remains, what guarantees that mathematics conveys truth, and how does it do so consistently? Meeting Pierre Cartier was an encounter with a personality who combined incredible intellectual rigor with an equally exceptional human generosity. His colleagues remember him as a man of great simplicity, whose altruistic pragmatism was as impressive as his vast mathematical knowledge. Anecdotes abound about his cycling exploits, demonstrating a physical vitality that seemed to defy time, and about his talents in astronomy, a field in which he enthusiastically shared his knowledge. On his approach to research, he says, Feynman once said that to be a genius, you just need to keep 10 problems in mind and constantly look for solutions in everything around you. My approach is rooted in my innate curiosity, which was nurtured from my early studies in philosophy, physics, and mathematics. I always tackle multiple problems and methods simultaneously, allowing me to draw analogies between different subjects, a process that has often led to significant discoveries in my career. My character was shaped by my father's boundless imagination and my grandmother's Alsatian common sense. This combination instilled in me an insatiable curiosity about people, travel, and reading on a wide range of topics. My wife, who had literary and musical interests, also opened up new perspectives for me, such as music, which I learned to appreciate thanks to her. Today, I continue to cultivate this curiosity, for instance, by collaborating with musicians on projects inspired by Euler's classical works on music. Cartier's legacy also includes his role as a mentor and educator. He inspired countless students and colleagues with his enthusiasm for mathematics and his commitment for intellectual rigor. His generosity in sharing ideas, his encouragement of young mathematicians, and his ability to see connections across diverse areas of study have left a lasting impact on the mathematical community. Cartier's influence extends far beyond his published work. He was known for his ability to ask deep, probing questions that often led to new avenues of research. His insights, whether shared in written form or in conversation, have sparked ideas and collaboration that continue to bear fruit in the mathematical sciences. At the IHES in Bourges-sur-Yvette, Pierre Cartier was more than just a researcher. He was a pillar of the institution, significantly contributing to its prominence. For those who had the privilege of knowing him, he was more than a colleague. He was a mentor, a guide, always ready to illuminate the darkest paths of research, to answer the most complex questions, or to place a problem in its proper conceptual context. His passion for sharing extended beyond theory. Pierre Cartier was an indefatigable traveler, putting his generous ideas into practice by teaching around the world, particularly in Vietnam, where he frequently visited to impart his knowledge. He also loved political discussions, particularly with Laurent Laforgue, and although their opinions often differed, they found mutual pleasure in these exchanges, reflecting Pierre's open-mindedness and intellectual vitality. Indeed, Pierre maintained his open-mindedness and dedication to engaging with and sharing ideas within the mathematical community throughout his life. In January 2020, Pierre delivered his last lecture, which took place at IHES. By that time, he preferred not to give lectures while standing for extended periods, so we adapted the format to make it more comfortable for him. To support this, we prepared slides based on a video of a similar lecture he had given in 2018. The idea was to play the video alongside the slides, allowing Pierre to pause it at any point to provide additional insights and explanations. The topic was fascinating, exploring a paper by Hiroshi Umemura and an idea by Yuri Manin on deriving quantum groups from Galois theory, framed in such a way that the Galois group would naturally manifest as a quantum group. The lecture went beautifully. Pierre answered questions, engaged in discussions, and paused as needed to further elaborate on the material. This final lecture in January 2020 was a testament to his enduring passion and enthusiasm, and he continued to enjoy being a part of the IHES community. As we reflect on Pierre Cartier's extraordinary career, We celebrate not only his mathematical achievements, but also the spirit with which he approached his work. His contributions have not only advanced the frontiers of knowledge, but have also embodied the essence of what it means to be a mathematician: curious, rigorous, creative, and deeply connected to the broader intellectual landscape. Cartier's life was entirely dedicated to the pursuit of knowledge, the exploration of mathematical mysteries, and service to the scientific community. His influence was considerable, and his legacy will continue to live on through his contributions, writings, and the inspirations he imparted to so many of us. Even in the face of illness, Cartier displayed exemplary courage, never allowing his physical condition to diminish his intellectual vitality. His example encourages us to pursue research and the dissemination of knowledge with the same passion and dedication that he embodied throughout his life. As Jean Cocteau wrote, "The true tomb of the dead is the heart of the living." Pierre will always remain with us in our hearts and minds, forever inspiring us with his immense contribution to the world of mathematics. Pierre Cartier had a great fondness for metaphors. It is interesting to note that his quotes describing his journey and love for traveling to teach mathematics elsewhere, not necessarily his own mathematics, but mathematics in general, serve as metaphors for his way of life and his joy in sharing his passion for the subject. I could describe myself as a mathematician without borders, borrowing from a well-known saying. By this I mean crossing boundaries, which allowed me to do mathematics in some rather remarkable countries: Vietnam, Iraq, Kurdistan, and others. Teaching mathematics in such places made the effort worthwhile. Why is it interesting to cross borders? Because on the other side, things are different. It's always exciting to venture to the other side of the fence to see what lies in the shade. What may seem uninteresting on one side can be a treasure on the other, offering a fresh perspective. Something that might seem trivial here could be significant there. So yes, I know a lot about crossing boundaries. They are meant to be crossed. From a scientific perspective, the start of my career took me across many frontiers. I began as a radio astronomer and, after a few detours into philosophy, ended up as a mathematician. To do good science, you need that constant imagination. No prejudice, and as I've learned from experience, no fear that your ideas might be silly. Acknowledgement: we would like to warmly thank Mark C. Wilson for his invaluable support and insightful suggestions during the preparation of this tribute. We're also grateful to Jean-Pierre Bourguignon for his meticulous reading, and we wish to acknowledge the referee's suggestion concerning Cartier's theorem. Well, that's very interesting and inspiring. It inspires us to go do some great mathematics. I'm Dr. Samuel Allen Alexander. Please like, comment, and subscribe, and I'll see you in the next video.